Hi, everybody, and welcome to the Thursday's live session for JuliaCon 2020. Um, First up, we have Jeff and Stefan, who really need no introduction, talking about the state of Julia in 2020. Take it away.
Hi, everyone.
Hi. So we're gonna give what it's actually the first time we've done something that's officially called the State of Julia, but we figured it's been a couple of years since 1.0, which sort of had a not called as such, but very big State of Julia where we announced and released Julia 1.0. So we're just gonna look back at some of the things that have happened since 1.0, what the big developments in the ecosystem and the language have been. And also look forward to what we have coming down the pipeline in the near and slightly less further into the future. So let's start with where we've been, past, present, then future. And Jeff is going to talk about multithreading.
Okay, so multithreading has been kind of one of the big arcs of the project. Initially, we didn't have any for several versions. And then in 0.5, we started adding a little bit. We had a simple loop parallel model at first, just flat parallelism. And then just last year, really, we announced an entirely new model based on spawn weight, which is a composable model. Composability, of course, is very important to us. I often read that word as compostable, which is, it's almost the same thing if you think about it. But so we've been working on this. It's starting to get quite widely used. I think over the past year, it's gotten a lot more solid. And one of the pieces of progress over time has been trying to reduce the overhead of the scheduler. In many ways, the scheduling overhead kind of limits what kinds of applications you can do and how much scalability you get, and sort of where this will be applicable. So I think it's going to be important to reduce the overhead over time. We haven't actually yet put a very large concerted effort into this, but we've been kind of chipping away at it part-time. And you can see where we've come since last year. So on a couple of simple micro benchmarks, just doing a bunch of spawn weight pairs, or then doing the parallel tree recursive Fibonacci, we've come down about 15–20%. So it's not bad progress so far, but we'll be doing a lot more of this. All right, so moving on to Julia Hacker News and Twitter bingo topics. This is something I think about every day. I worry about it every day. People are always talking about the latencies that you get in Julia. The infamous time to first plot problem. So this is something we've been focusing on a lot, actually. There actually has been quite a concerted effort in recent months to try to address this. And this is not a small problem. This is not something where we can just kind of go in and fix the bug. It has to, many things have to be done, some small, some big, on many different levels. So if you look at the latency label on GitHub, which this label hasn't actually existed very long, but you can see there over the past, I don't know, year or so, 66 PRs have gone in related to that. This is actually an underestimate. I realized that we're not perfect about tagging things, so it's actually a few more than that. So it's been quite a few different things have to be done to try to work on this. So let's look at where we've been. You can see for several versions, basically nothing changed. So from 1.0 to 1.4, you can tell we weren't working on it pretty much by looking at this graph. And in fact, unfortunately, it looks like 1.4 got a little bit slower. So sorry about that. That's unfortunate. But yeah, it hadn't really improved. And then you can see that in 1.5, there are the fruits of our efforts. So that time is now starting to come down significantly, and master is even a little bit better. So we are chipping away at this as well. So there's good progress happening here.
And I want to point out that this time to first plot is sort of a worst case here. There's a lot of other load times that have gotten substantially better than this because they're not quite as complicated and involved, and they don't involve quite pulling so many pieces together. So I'm going to talk about the debugger because this has been sort of one of those bullet points that everyone seems to want for a programming language, and I can understand that. I love using a good debugger as well. And technically, we've had a debugger since 2017. In November 2017, the first release of Gallium came out. So Gallium was the code name for a LLVM-based, sort of GDB or LLDB style debugger that Kenno Fisher worked on. He spent a huge amount of time and energy on this. And I think, his quote, he was commenting on the new debugger made it on Hacker News, and he wrote this comment. The whole comment is actually really interesting. I think it's the most self-reflective about what went wrong with Gallium. But this was his statement about it. And I think, it was a great effort. We learned a lot. We got a lot of great technology, but it was ultimately a little bit too ambitious and ended up not being as useful as we wanted it to be. But fortunately, Kenno's great work was taken over and advanced further by other people: Christopher Carlson, Tim Holey, Sebastian Fitzner. And Debugger.jl was released last year. And so this steps back and takes a much simpler approach. It's interpreter based, which means it's slow, but it's very, very reliable, very straightforward. Things work the way you intuitively think they should work, which, if you understand anything about the internals of a compiled programming language, things don't actually work the way you intuitively think they work. They're just carefully arranged to make it look like that's what's happening. But in Debugger.jl, it actually is doing the naive thing that you think it should be doing. It's very full featured. It can do all sorts of different things, and it's really reliable. So those are the sort of three features that make it actually a very useful debugger. The big problem with it is just that because it's based on an interpreter, it's pretty slow. So if you have to run a lot of code that is computationally intensive, or even just does a lot of I/O, to get to the point where you want to be debugging, that can take a really long time. And so that's a stumbling block for a lot of people. But we're hopeful about improvements, ways to improve that. We're actually trying to schedule a meeting of sort of the people who have their fingers in this pie for next week, and hopefully we'll make some progress. And you can see the really nice UI for the debugger on the right-hand side. I think this is this VS Code or is this Juno? I'm not sure. It's one of the two.
This is Juno.
This is Juno, okay. So both Juno and VS Code have a really nice debug, UI for this type of thing. So one of the big advances in Julia 1.0 was the package manager. So there was a total rewrite, and we went from having a sort of traditional, relatively run-of-the-mill package manager like what you'd find in, Ruby or Perl or Python, although built in and standard. So that's an improvement over some of those systems. This was called Pkg 3. So if you ever see that, that's what it's referring to. Third generation rewrite of this. And the high level concepts are, just out of the box provide per project environment, so that when you're working on one project, you can have one set of versions of all your dependencies. And when you switch to another project, that isn't dictated, it isn't dictated that you have to use the exact same set of versions, because why would that be necessary? Also, being able to record all your dependencies was a huge deal. That's a big goal of the system. And then also track them in version control so that you know what you were using in the past potentially. And then also to make it reproducible forever. So, you record this information and it shouldn't depend on some other third piece of information that can change over time. So in Julia 1.0, the way this was accomplished was with project and manifest files. And they together record the full dependency graph of Julia packages for your entire application. And this has been wildly successful. People can email, manifest files around to each other to get the same setup in exact same setup environment and test things out and reproduce bugs. You can check your manifest file into the version control of your project and reproduce exactly how it was working. And today we have, in this new system, 4,000. I think we hit 4,000 yesterday. Registered packages. So that's, really exciting. In 1.3, we introduced a new concept, which is artifacts, and then Binary Builder is a way to produce artifacts for platform-specific binaries and libraries. And this extends our tracking of the full dependency graph and reproducibility all the way down to the binary dependency level. And that's been wildly successful. We've sort of gone from a situation where it's pretty common for people to try to build libraries on their clients and it just doesn't work for whatever reason, to things just work because all these binary builder artifacts do is they're just tarballs that unpack, and they should work on your system. And now, I mean, we've had huge progress in, I think, less than a year. We now have 470 binaries wrapped, which is huge. We're well on our way to having our own sort of cross-platform Linux distribution going on here. Julia 1.4 introduced something called the Pkg Protocol, which wasn't on by default in 1.4, so I'll talk about it a little bit more later. The ecosystem has come a huge way in the same amount of time. I think one of my favorite recent examples is csv.jl, which went from sort of an underdog CSV parser in the grand scheme of things to now being best in class. Like it's the fastest CSV parser in the world for most CSV use cases.
And it's multi-threaded, which I'm very proud of.
And
and Jacob Quinn should be proud of.
Well, it's great to see the way that has panned out, right? Like Jacob was able to take CSV and relatively easily turn it multi-threaded by using the infrastructure that you and Jameson created for threading. The SciML org for using differentiable programming to do machine learning in scientific applications seems to be growing exponentially. They already have 95 repos in their GitHub org, which is just incredible.
Yeah, it's huge. I mean, it's more than JuliaLang. It's more than a lot of things. Yeah, it's really incredible.
It's really an epic project, and there was a great talk about it yesterday, which I encourage people to check out. There was also a talk about Juno and VS Code yesterday that Sebastian gave. They've joined forces is the short story. VS Code is going to be the future because Microsoft has purchased GitHub, and so the Atom editor is kind of winding down, and VS Code seems to be the way to go.
Yeah, I'm very excited about this because for a while now we've actually had two good IDEs. Juno and VS Code for Julia were each independently quite good, and so to hear that those two teams are going to be working together on a common system is just incredibly exciting because I can only imagine where that's going to go. It's going to be amazing, I think.
Yeah, I agree that no longer splitting our forces in the IDE front is going to be a powerful force, I think. These days, you can actually, people are writing, serving websites and writing servers in Julia. That's a thing. I've written several myself. The server component of the Pkg Protocol is written in pure Julia. The core library there is HTTP, but there's great frameworks on top of that, like Genie and Franklin. All of the Julia docs for Julia itself and for a lot of packages are generated in Franklin. It's a really great system. And I was pretty frustrated in the past with Jekyll, so it's really nice to have a system that just works, and also, bonus that it's written in Julia. There's a great talk yesterday about Pluto.jl. So that's a new notebook system. So kind of think similar to Jupyter, but with a reactive programming model, which basically means that's too hard to explain here, but it's similar to observable notebooks, if anybody has heard of those. So it's a very cool bit of technology. The GPU system has gotten more and more robust and mature. I think one of the big developments there is that now you can install the GPU drivers more easily in Julia than anywhere else, because it uses all of that whole artifact system. So now you can just sort of install CUDA packages and you have a working GPU driver immediately, which is kind of mind blowing, honestly. JuliaHub.com is a site offered by Julia Computing, and today it's really mostly a place to find and search Julia packages. You can have search by code and all sorts of other stuff, but in the near future we're going to allow you to develop your code locally and then just click a button to run it in the cloud. Which, for example, in the Julia computing demo yesterday, Matt Bauman gave a demo where he had run some alpha 0 code locally, which would have taken a day or something like that, and then he ran it on a beefy GPU machine in the cloud, and it trained in like 2 hours, which is pretty amazing. I think this is Jeff's most favorite recent discovery, which is that there's a Julia typeface.
Yeah, I think this is super cool. I mean, this is I just think it's cool. It's something I never thought I would see. I immediately started trying to use it right away, and I've already filed an issue, so you can do that. It's pretty cool to be able to file an issue on a typeface on GitHub. So this is just a fun thing. There's a lot of recency bias in this list. I put some things on here based on just what I've seen at JuliaCon already, which you can probably tell. But there's but we need some way to create a small sample of what's happened, because it's just so much. So this is really just a small biased sample.
Mm-hmm. Was it a kerning bug? Was that your issue that you filed?
No, it's not. But you can go check it out on the repo.
Yeah. All right. So where are we now? What's the current state of affairs? Well, version 1.5 is nearly out. The second release candidate is already out. So please try it and report any issues you find. Hopefully there are no showstopper issues, and the second release candidate might actually end up being the final version.
Yeah, I have high hopes that RC2 will become final sometime, maybe early next week. Fingers crossed.
It's been a very smooth release so far, so fingers crossed this might be the last one. Okay, so there's been a little bit of progress on multi-threading. You want to talk about it a bit?
Yeah, sure. So I'll say also at a high level, I think since we've been doing timed releases, we never know exactly what we're going to get in any given release. And I think what 1.4 was fine, but if you browse through the release notes, it's not really very big. It's sort of it's a ho-hum release, solid, but not that much that's very exciting. 1.5 I think is really different. There's a lot of really great stuff in 1.5, so it's going to be great, I think. Yeah, multi-threading. There aren't really many new features. There are a couple new features actually, but we're basically declaring parts of the API to be stable. And we, instead of just saying it's experimental, don't use it. Instead, we've gone through and tried to carefully document, where all the sharp edges are, so that we can signal that it's really ready to be used, because really a lot of people are starting to use it. Okay, so now one thing I hear a lot, a question I get a lot is, is Julia as fast as C++? And if not, why not? And so there are a couple reasons. So first, of course, it depends what you're doing. I mean, sometimes it is as fast as C++. Handful of reasons why Julia might be kind of generally slower than C++. And one of them, of course, is heap allocation. Like most high-level languages, Julia will tend to heap allocate a lot more objects than a C or C++ program. But not anymore. So we have a really nice optimization in 1.5 that eliminates a pretty large class of struct heap allocations. So for instance, in this example, just a micro benchmark, I have an array of arrays, and then I do a product iterator of that. So I take all combinations of those arrays and collect them. And so in 1.4, we had to allocate all of those tuples. So that allocates 1 million tuples. It takes a bit of time. In 1.5, those allocations are gone. We have O of 1 allocations, and it's 7 times faster. So this is just fantastic. This is going to really help a lot of abstractions work with no overhead. This also affects array views a lot and subarrays. So you can kind of use those without fear now. And just it's a whole category of abstraction overhead that is gone. And I have to thank Jameson Nash for doing a lot of the work on this, and Relational.ai, which sponsored this work, because they recognized how important a category of abstraction overhead this was to remove. So they sponsored this project, and it's done, and it's in 1.5.
I think the true sign of this being an epic transformation in the language which sounds like a big deal, but my criteria for that is that it eliminates a whole class of workarounds, right? In the past, we've sort of had these watershed moments in the language, like when functional programming, higher order functions became efficient. Suddenly people stopped doing all these workarounds and just started using higher order programming without fear. And I think this allows us to do, view-oriented programming without having to worry about the performance implications. And that really, that changes the feel of the language in a way that I think people are only starting to realize when they're using 1.5. Another big change, well, so, 1.0 had a lot of changes. Most of them were pretty well received. I'd say almost all. There was one that was not so popular. So you can see a demo here of it in the Julia REPL. You assign, to an accumulator the value 0, and then you try to accumulate to it in a for loop, and you get this inscrutable error message, S not defined. Okay, well, why does this not work? Well, it's obvious to us looking at this little bit of code that this ought to update S. But coming up with language rules for these things that work well in all cases is not so simple. We used to use a heuristic for this in pre 1.0 that worked pretty well, but it actually caused a lot of bugs because sometimes these statements are pretty far removed from each other. They might be in different files. It's often the case that you kind of, you assign temper to a variable name like S in a for loop, and actually you just only use it inside of the loop iteration. But if there happens to be an unrelated variable named S that's global, this could cause bugs. And that's not hypothetical, it actually did. When we changed this in 1.0, we discovered a huge number of bugs, both in base Julia and in packages. So fixing this was good, but it's really annoying. People find this, they want this to just work in the REPL. They're confused when they encounter it. So we've had a lot of back and forth about this. So now in 1.5, here's what happens. In the REPL, it just does what you want it to do. So that, that inconvenience is gone. You can cut and paste from inside a function body into the REPL and it just works. However, we don't want to break code that's out there. And also we like the fact that you don't accidentally clobber globals if you, assign to them inside of a for loop in some other file or wherever, some later in the same file. So in a file, you get this very clear warning that says that this situation is ambiguous. And the reason it's ambiguous is because, it's unclear whether the inner loop, the S inside the loop should be a new local or overwrite the global. So now you have a warning and you have to say either that it is explicitly a local S or a global S to silence the warning. So what we like about this new design is that it recovers the convenience and usability of the pre 1.0 behavior that some people remember, but it also retains the 1.0 safety against accidentally clobbering globals. So we sort of get the both best of both worlds here. The only downside really being that it's a little complex and it's a little annoying that it is slightly different in a file or REPL, but I think this is a really good compromise.
And I want to add also that was quite a long and I don't know if I should say agonizing, but design process. We really went through a lot of possible ideas and alternatives, and for about about a year, quite regularly Stefan would Slack me, okay Jeff, it's time to talk about the scope issue again. And
yeah, I could tell you were dreading that every time I was like talk about the scope issue.
So it was quite a drawn out process to get there, but I think it came out the right way.
You prototyped, you had a fully working PR of a prototype of a totally different solution.
Yeah, we fully prototyped at least one or two, different full approaches,
which we decided was too complicated and too hard to understand. And I think that was worth exploring, but I'm glad we went with the way we did because I think this is much simpler and clearer.
Yep.
Okay, so we talked about the package protocol a little bit earlier. So in earlier Julia's, the package manager just downloaded packages from wherever they're hosted. GitHub, GitLab, Bitbucket, personal servers. It can really be, it's usually on GitHub, but it can in theory be anywhere. So if you need to access all of your registered packages, you potentially are talking to any server anywhere on the internet. it can potentially use different protocols, the Git protocol, SSH, plain HTTP, secure HTTP. This was like a really practical way to bootstrap things and get things going, but it's actually not super great in the long term. So here are some of the issues. So the worst one, I think, is probably that resources can just go away. So, if people remember the left pad incident in the NPM JavaScript world, if someone deletes a package from GitHub, then, it's just gone and nobody can install it. So that's not great. We also don't get any download stats. So that's unfortunate, because it would be nice to know what packages people are installing and using. It's tightly coupled with GitHub and Git. There's a lot of features that GitHub hosted packages get that other ones don't. And, also it's sort of inherently tied with the Git protocol, which is unfortunate too, because people sometimes develop things using non-Git version control systems. Terrible for firewalls and sysadmins, because you're potentially talking, all these different protocols to all these different servers. And finally, it's, bad for speed and bandwidth. If you're in North America, it's pretty okay, but I've heard of horror stories of people in China or Australia taking tens of minutes to update their packages, which is really unacceptable. We want everyone everywhere to have good performance. So the solution is a thing called the package protocol, and it's just a really simple HTTPS protocol for package clients to get resources that they need to install packages. And you can see a little sort of, this is what the HTTP requests look like. It's pretty straightforward. I gave a talk about it yesterday with Elliot, so check that out if you're interested in more detail. And in Julia 1.5, this is now the default. This is how people by default get their packages. They talk to a server called pkg.julialang.org. And it's, it's not a real website. It's just a resource server. And the server side is implemented in Julia. It's open source. You can see it in the URL here. So, check it out if you're interested. And we operate a network of these around the world. So here's a little map. And there are 10 package servers, which are the red and the green are both package servers. And then there's a thing called a storage server, which is basically a persistence layer behind the package servers, which are just caches. And we have 2 of those on opposite ends of the planet. So this is probably going to grow. We want to cover the entire world, but it depends on where AWS offers certain services. So as soon as that expands, we'll be everywhere. All right, so now we're going to talk a little bit about the future.
Yeah, so latency is still a problem. We don't think by any means that 10 seconds to 6 seconds is victory. It's nice, but we need to do even better. So there are actually a lot of tricks still left in the bag. We haven't done everything we can possibly do. We can make the JIT compiler lazier. We can try to make the interpreter faster and use it more instead of taking the time to compile things. We still don't cache native code for packages, so we could potentially do that. And recently, Tim Holey has taken on the role of invalidation czar, who's trying to reduce the number of times we recompile things, which is another source of latency. So there are a lot of things that are we can still do and are still ongoing to improve this. Task and thread system is still getting a lot of work. Overhead has come down, but needs to come down a lot more. I'm hoping we can do more of a concerted effort on that in the next year or two. We're thinking about better debugging features to make it easier to see what's happening if your tasks are stuck or something goes wrong. Control C is always a big problem. In a program, you try to reason about which sections can't throw exceptions, can't be interrupted. If you have Control C, everything can be interrupted. It sort of makes it impossible to program on some level. But we're going to try to improve it as much as we can. There are a lot of discussions about different concurrency primitives, context variables. Takafumi has a whole really interesting set of ideas about this, where there's a lot of discussion going on. And we still need to integrate with multi-threaded BLAS. We've done that for FFTW because Steve Johnson was able to help with that, but we haven't done it for BLAS. It's something we need to do. And we've also focused so far on throughput, essentially, but we need to do more to help latency-bound workloads and working better with GUIs and real-time kind of stuff. There's also a lot of compiler work happening. So We have kind of a goal of making the compiler more extensible and reusable. There have been kind of some experiments and kind of special case projects over the years, like the GPU compiler is one of the best examples of something that kind of tries to reuse and retarget the Julia compiler. That's been kind of a pioneering project for generalizing the compiler, but we need to make that sort of more generally usable, so we can bring more kinds of alternate backends online and we can do more things with code. So cassette.jl was another kind of very important concept that was invented to kind of realize the compiler and be able to rewrite code in various ways. So we're currently looking at, Keno mostly has been working on a way to sort of generalize the compiler and make it easier to do these kinds of things. And we have target use cases like better automatic differentiation and such. We've also just barely started thinking about, and there's been no work done on this really yet, but it's just kind of an idea that I'm very interested in, which is to basically add some sort of a separate compilation model to the language, which you can think of as being a bit like package compiler, except you can compile multiple things, just like you would from C++, make multiple .so files. And you can have something like a header file and have them link against each other. So more of a traditional kind of separate compilation model, I think, is something we can add to the language and should. Haven't started on it yet, but it's something I'd like to do.
So we're not done with the package manager features. 1.6 will include actually a pretty big, significant list of improvements. Some due to me, but most of these are actually Elliot Saba's work. And if you want more detail, we gave a talk yesterday. But so, we send resources from the package server to the package client, but you can do that faster if you know what the package client already has. You can send a diff instead of sending the whole thing. So that'll give people faster updates. Currently, artifacts, binary artifacts have a slight problem with load time. Basically, we end up loading them all right up front, which takes a while and isn't necessary all the time. So he's reworking the way binary artifacts get loaded so that, your Julia packages will load faster, which, nobody's going to argue with, obviously. Scratch spaces and preferences are basically two features designed around avoiding having to mutate the state of the package itself. So some packages kind of use their own directories as a scratch space, a place to like save some data that they've downloaded or whatever. But that's not great because you want your packages to be perfectly immutable and perfectly reproducible. So scratch spaces are a first class way of providing packages with a little bit of room for mutable state, that it's okay if it goes away because they can reconstruct it. And preferences are just a way to globally configure your packages on a system. So this all brings us to, what's next? And basically the thing we've realized is that, the king is dead here. Julia 1.0 is a little bit past its prime. It's still perfectly usable, but it's getting really hard to support it for new packages because there's just too many new language features that we've introduced since 1.0. And it's also, on our end, getting really hard to backport fixes to it, right? So we have fixes for known bugs, but we fix things on master, and then, if the difference between master and the 1.0 branch, it's gotten pretty huge at this point. So it's really, really hard to backport fixes. So it really seems like it's time for a new LTS. And so we're officially announcing that Julia 1.6 will be the new long-term support version of Julia. One little detail here is that 1.0 will remain LTS until we branch for 1.7. And the reason for that is that we always have two active backport branches. So if 1.6 was the LTS when it came out, then we'd only have one backport branch, which is not how we want this to work. So 1.0 will remain the LTS and keep getting backports until we branch for 1.7, and then 1.6 will become the new LTS. So because of this, we're going to slightly change the way we do releases. We've been doing timed releases, and the system that we've converged on is that we we time the feature branch. So basically we say no new features on this release, and that's timed. And then it takes however long it takes to stabilize it and release it. So, you know, you can't rush the release. If there are bugs, there are bugs. They have to be fixed. But what you can time is you can time when you say no new features on this branch. But for 1.6, we're not going to be doing that exactly. So we're still going to try to keep it on schedule, but you know, we will wait for necessary features to be ready, because this is going to be the version that we have to live with for a fairly long time into the future. So you can think of it like a little mini version of the 1.0 release. Not as many things and not as, you know, much pressure, but we really, you know, we want to get this one right. Overall, I feel like there's been amazing progress, and there's, you know, even more exciting things coming down the pipeline. I really want to emphasize that, you know, this is not our work. This is the work of the community. So many people, some of whom we've mentioned in this talk, others who we haven't mentioned, but, you know, the bulk of this is done by, you know, hundreds and hundreds and maybe even more people who do incredible work throughout the community.
Yeah, so Julia language itself, for example, passed 1,000 contributors not long ago.
Yeah, that's a pretty great milestone.
Yeah, so thank you, all 1,000 of you.
And our ability to work on Julia, you know, and, you know, make it what it is and contribute to all the open source projects that we get to contribute to is made possible by our company, which we founded, but, you know, it still makes it possible. It's Julia Computing. And so, you know, check out the sponsor talk from yesterday. It's an actual technical talk about Alpha Zero. So it is actually interesting. It's not the usual, you know, marketing only stuff. You know, the products, you can read them here, but there's going to be a demo tomorrow at 7:45 p.m. GMT, which I'm not going to try to translate that EDT or whatever, but you can figure it out yourself. And always, you know, chat with us. There's a Julia Computing channel on Discord, or, you know, the Julia Computing website has a chat box.
Thank you all for watching.
Yeah, thank you so much, everyone, for attending this. And I think we have time for some questions.
Yep. Thanks again, Jeff and Stefan. So I've got one question from Discord. In the tasks improvement work, I don't see a tasks priorities or support for a main thread. Is this covered in the bullet for latency bound workloads? In particular, just as an example, in Jacob's microservices workshop, he created his own scheduler specifically to avoid starving the HTTP server task.
Yeah, so I think some of that would hopefully be addressed by the latency part of it. I don't know if it would be implemented by like explicitly selectable priorities, like numbered priorities. I don't know if that will be part of it, but I think the latency stuff will address that. Yeah.
Right. So one question I had, given how Julia is designed, what do you think is the best you can do about compile time? So what is the best case scenario in terms of, you know, of course, you need to you know, run type inference and everything, right? When you run the code for the first time. So what is the best case scenario that we can expect?
It's hard to say. I mean, I think another factor of 2 is definitely achievable.
But I think that's using sort of specific, you know, specifically the approach of how fast can we make the compiler. There's all sorts of tricks that can be done beyond that, right? Like you can, for example, have already compiled the thing and then people don't care about latency. So that's
Yeah.
the separate compilation work would address that angle. You know, there's other
most of Julia can't really be separately compiled the way people use it. So the latency, the compile latency stuff, I think is going to continue to be important. But yeah, so things like caching native code could potentially reduce it quite a bit.
I mean, there's also, we currently are an ahead of time JIT compiler. That's not necessary. You know, a lot of JIT systems don't do it that way. They actually interpret immediately until the compiled code is ready. And then, you know, you basically get the best of both worlds, but at the cost of unpredictable compute, you know, a less predictable compute model, but that's, you know, that's always a thing that could possibly happen in the fullness of time.
Yeah, and we can have a switch to turn that on and off if it, you know, if it's not good for some workloads.
Yeah.
But yeah, quite a bit is possible.
All right.
All is
yes,
possible with enough time and money.
Well, thanks again, Jeff and Stefan for for a great talk.
I think
I just
Stefan should be our new nickname as a unit.
Yeah, it should be. Yes. Yeah, but on this note, I wanted to move on to Tim Holy, who will be presenting the Julia Community Prizes.
All right. Thanks again, Jeff and Stefan, for a fantastic and exciting talk, both about where we've come and where we're going. I am here as the representative of a committee of Alan Edelman, Curtis Vogt, myself, who have the exciting task of selecting award winners for the Julia Community Prize. And these were, we solicited nominations, and we got a very large number of nominations. And one of the things that, you know, I think I hope everyone understands is that, you know, it's a very difficult thing to choose. There's so much exciting work that's going on in the community by so many fantastic people that you know, choosing is a very difficult task. So if you aren't awarded today, despite Herculean and really important contributions, just wait. We're still hoping to get to you. We really have a long list of people that we'd like to be able to award. So we're awarding 3 people this year. The first is being awarded because of his work on supporting Julia's ability to interact with external libraries, Binary Builder and Yggdrasil, and also providing outstanding support on user forums. First prize goes to Mose Giordano. Yay. The second prize is given for a remarkable package, Loop Vectorization, which delivers state-of-the-art performance on a growing range of demanding computational tasks. And he also has very effectively instructed the community on the myriad factors that determine CPU performance and how to improve it. The second prize goes to Chris Elrod. And the final prize is for her contributions to growing the community through an outstanding series of data science courses and for her outreach to many other organizations evangelizing Julia. We award Huda Nassar. Thank you all for your remarkable contributions to the language and the ecosystem and the community that we value so much. I also wanted to say that we're thinking of making some changes to the community prize next year. There have been a growing number of cases where we've noticed it's difficult to choose one person who's contributed to something. And so we're thinking about trying to grow the prize to include teams of people next year. And these are monetary prizes. And so we want to be able, if at all possible, to boost the amount of the award we can give out also when we award more people. So this is all something we're going to be discussing over time. But if you have financial resources and are interested in supporting this, we hope to talk to you about this. So anyway, thank you very much. And I look forward to an exciting next year from the community.
Thanks very much, Tim. Logan, would you mind introducing Juan Pablo for our next keynote?
Sure,
we are
6 minutes ahead of schedule.
Yes.
We are 1 minute ahead of schedule. Yes, that's right.
My timer says that the keynote should start at 10:10, my local time, and it's 10:04, but I'm happy to get started in 1 minute if everyone else is.
We have, no, we should wait. We have a 5-minute gap between the two. So let's just take that break. So anybody watching on YouTube, we will be back in 5 minutes. Juan Pablo, do you want to share your screen, please?
Let me see. Share screen. Is it working?
Yes, it is working.
Perfect.
We are still going live on YouTube from the previous talk, but we should wait till 10 past the hour and get started with this one.
Okay, sounds good.
So about 3.5 minutes now, but I can see your screen clearly. Thanks. "30 seconds, Logan."
Perfect.
Take it away, Logan.
Awesome. Hello, everyone. We are super excited to kick off our second keynote address for JuliaCon 2020. We are joined by Juan Pablo Vilma. Juan Pablo Vilma was previously a associate professor in operations research and statistics at the MIT Sloan School of Management, but he just informed me he is currently in a new position as a research scientist at Google. And Juan Pablo is also one of the key contributors to the jump.jl package. So Juan Pablo, kick it away.
Thank you very much. So it's really exciting to be giving the keynote. It's actually my first keynote and my first online presentation. So hopefully it will go well. So, and what I want to talk about is basically conic optimization in Julia and Jump. And so basically, I guess the easiest way to know what conic optimization in Jump is by going to the Jump tutorials and clicking on the conic programming notebook. And you'll find the first example is a very simple optimization problem that's trying to find, basically project a point onto a hyperplane. And this is how you would write it in math, but it tells you, well, if you want to write it in Jump, you actually need to do a little bit more work. And basically, instead of just working directly with the norm, you need to work with the cone or the epigraph of the norm function, which is the Lorentz cone or the ice cream cone that you have right here. And if you look at the Jump code, it basically looks very similar to the math here. You need to write down, instead of writing down a norm in the objective, you're writing some vector that has to, you're asking it to belong on the second order cone, which is again, this ice cream cone over here. So one of the things I want to talk about is like, well, why are we doing this? Why couldn't we just write down something with norms? Couldn't we just use the nonlinear interface in Jump? And you can still do that, but you could actually get a little bit of extra power by doing the conic formulation using this particular form. So I want to talk a little bit about is like, why is it that this conic formulation is more interesting? How did it become one of the most important ways of writing optimization problems in the current versions of Jump? And in particular, one of the solvers that was very focused on conic optimization was the Pajarito solver. And it currently only works on Jump below version 0.18. So I also want to mention, like, why is it that this hasn't changed yet? There's going to be a lot of like mathematical details that I won't have a lot of time to cover. So I'm trying to put links to everything, to notebooks and tutorials, like the Jump tutorials, everywhere through the slides. So and I'll share the slides later in case you cannot copy the links. So going back, what is conic optimization and how is conic optimization handled in Jump? And again, in the conic programming notebook in the Jump tutorials, it explains that a conic optimization problem is this optimization problem that's written as maximizing some linear function over many of these conic constraints. And the generic form is you have some affine function of the variables, and you're asking it to belong to a given cone. So it could be the Lorentz cone that I showed over here, and there's a lot of extra cones that you can have. In particular, one cone that is actually very powerful and useful is the cone of all positive semi-definite matrices. And if you use that cone, you could, for instance, write down a very, very simple optimization problem in Jump that tries to find the largest eigenvalue of a symmetric matrix by just writing down the constraint of this given matrix is in the positive semi-definite cone. So this is a little bit of a, I guess it's like a toy example, doesn't really show you what you can do with conic optimization. So let me start with a little bit more interesting example. And this is an example that I've been using for a while, since the beginning of pajarito.jl, basically. And this example is actually slightly more. So it's a conic optimization problem, but in addition to the constraints that I'm allowing you to use here, I'm going to allow having extra constraints that say some of these variables are going to be integer. And that's going to give us a little bit more modeling power to be able to like build a little bit more interesting problems. And the problem that I'm looking at is basically the control of a drone, so some automated drone. And I want to control this drone so that it avoids some obstacles that are shown here in blue. And the way that I'm going to describe the trajectory of this drone, I'm thinking it just in 2 dimensions. It's going to be its position with respect to time. And I'm going to expect that the position is going to be a function of time, some continuous function of time. It could be a polynomial, but the polynomial won't give us enough freedom to be able to add avoid the obstacles. So I'm going to go a little bit further, and I'm going to sort of discretize this by saying I'm going to divide the time period. I'm assuming the time period goes from 0 to 1. I'm going to discretize it in it's separated into some intervals, and in each interval and each sub interval, I'm going to request that the position as a function of time is a polynomial on t. Okay, so that's going to give me a lot of freedom on how do I actually describe the trajectory. I'm going to easily be able to restrict the derivatives and things like that. But in addition, by doing it piecewise, I can actually incorporate discreteness to try to avoid the obstacles. And the idea is very simple. Instead of trying to avoid the obstacles, I'm going to delineate these green boxes that could be boxes, but could be general polyhedrons, which are places that I know are safe. As long as I'm strictly contained in one of these boxes, I'm not going to run into any of the blue regions. So my safe constraint will be, well, for each one of the intervals, whatever polynomial you're using to describe the trajectory in that interval, that whole polynomial has to be contained, that whole trajectory has to be contained inside one of the boxes. I don't care what box it is, but it has to be at least one of the boxes and only one. So this constraint looks sort of complicated. I'm asking for a polynomial to be inside a box, but I can transform that and realize that, well, if I basically put the polynomial inside the polyhedron, multiply things around, my constraint is going to look like some polynomial in T, slightly different, needs to be greater than or equal than 0. So it still looks very infinite dimensional. It's kind of hard to work with, but there's a technique known as sum of squares, which basically tells you that if you want this polynomial to be non-negative in the interval, you basically can ask it to be, it's nearly equivalent to asking for it to be a sum of squares of some other polynomials. And if I go and restrict the degree of the polynomials, I can write down this with several extra variables and make it so that it's a semi-definite constraint like the simple one I described over here. So, and there was a lot of math here, so here's some links that explain more details on how do I get to that. But basically, I got through sum of squares to write down this problem as a mixed integer semi-definite perming problem that Pajarito could have solved. And these are some results that Joey ran back in 2017, and basically he used polyjump to basically write down a polynomial optimization problem, sum of squares.jl, transform that into SDP, and then we can solve it with the MISDP solver Pajarito. And you could do interesting things like make the avoidance problem while making somewhat of a smooth trajectory, or you could do even like more fun things like it's like Joey called it the helicopter problem, and I was thinking it kind of looks more like the Flappy Bird problem, where the dynamics makes it so that the point wants to drop, and every time you click, you basically give it a boost up, and you can try to say minimize the number of clicks that you need to be able to solve this. And even back then in 2017, it solved fairly fast, even though it was like a complicated mixed integer problem. So for that, there was, as I mentioned, there was a lot of links that you needed, that potentially needed to follow to understand all the steps of the math. The interesting thing is that, well, you might not even need to really learn all the Conic optimization steps that I'm giving you, because if you look at the polyjump code for modeling this, you'll see that basically it's defining polynomials and writing the constraints in a way that looks sort of how you would write the math. And in no place you see Conic explicitly. So polyjump.jl and sum of squares.jl will make all the transformations to make it work. So you could try it without necessarily having to understand every single one of the steps. And in addition, if you actually want something that looks more like expression or NLP-based modeling, there's a technique or a modeling technique called disciplined convex perming that allows you to follow some simple rules, and it will do the automatic transformation for you to a conic form as well. And that's available through convex.jl in the Julia environment. Now, still, so one of the things I like about Julia is you can start playing with it and try it, and then you can sort of like start peeling the onion and kind of know what, well, I'd like to know more what is behind and why this thing is working. So let me tell you a little bit about that. So the first question is like, well, why conic? Why do I go with the complication of writing a conic problem instead of just using functions or expressions? And one of the most interesting things is duality. If you write down a general nonlinear optimization problem, you can have like range and duality. Somewhat you can interpret it, but not that easy to understand the sort of like an intuitive meaning of what this primal dual pair looks like. But for conic optimization, the primal dual looks almost exactly the same as what you would have in linear optimization or linear perming. And again, you can see it in the conic perming notebook. And the very nice thing is that it allows you sort of an explanation of what are the limits that actually to optimality. Why can't I actually maximize or minimize this more? So you get things, you could get things that look like max flow min cut theorem or Mengenberger theorems that will allow you to understand what are the blockers to get something more out of your optimization problem. And in particular in polynomial optimization, it has some very interesting connection to measures, and you get go slightly further with things that look more closer to what jump will do. So instead of just cones, you could also have like a slightly more complicated sets. And if you want to know more about that, actually, the great thing is like Benoit Lagat, who's one of the core developers for Jump, recently graduated. So congratulations to Benoit. And you can actually learn a lot more about this duality and geometric interpretations of duality on his PhD thesis that you can find in his webpage. So it's nice from an interpretability perspective, but you could actually go a little bit even further. And one of the reasons conic duality is useful is for actual algorithms. It immediately improves it allows for more complicated or more effective interior point algorithms for conic optimization. And I'll talk a little bit about that later. And in particular, this is one of the reasons in 2018, there was a little bit of a shift from some of the more important commercial solvers for continuous optimization. And they basically switched to a more conic centric point of view. So Nitro, for instance, added support for second order cone constraints. And Mosaic basically deprecated all the expression or function based formulations and focused purely on conic optimization. And in particular with a small number of cones, but this small number of cones is basically enough to almost model whatever you would want to model. So, and the reason they did this is because it actually, it makes the solvers more stable and allows you to actually get much faster solvers. So, and this whole sort of shift from conic has been very tied to sort of the history of how Jump's been evolving. So for the first Jump developers workshop we had in Cambridge, the first two talks were basically Miles was telling us about Jump and MathProc Base, which is sort of the back end of Jump at the time. And then we had Chris that was telling us basically how Pajarito actually uses and connects to MathProc Base to actually make everything work. Interesting enough, the next day we had Benoit telling us about sum of squares, which was one of the first places I kind of saw the interesting or the potential for these type of modeling paradigm. And interesting enough, I guess we were already ahead of our times. That was a remote presentation that Benoit gave at the workshop. And I would say here is exactly where sort of the shift to conic potentially started with the conversations of the people that were there. And the following year in 2018, in the second workshop, we see that it actually had a lot to do with conic optimization. Math op interface was introduced as the new backend to Jump, which was very centered to things that look like conic optimization or even generalizations. Benoit introduced or was presenting about reformulation of these problems using constrained bridges, which is a key that actually makes it easy. You don't need to worry too much about what cones you have available, the solver has available. And we had a lot of, we had people from the actual two solvers that I mentioned, and a lot of applications and solvers related to conic optimization. And well, and MathOpt interface introduced a new sort of something that looks very similar to this, a find function that belongs to a cone, but slightly more general is like function in a set that includes the conic paradigm, but also includes a little bit more. And in particular, currently MathOpt interface function in set approach allows a whole bunch of different types of cones, including I guess if I find it, the second order cone is around here, positive semi-definite is around here, and you have a lot of extra cones, and there's a few extra sets that you could have that are not necessarily conic, but MathOpt interface will also understand. So great, basically the thing that Pajarito was waiting, the reason Pajarito worked on the before 0.18 is because it was connected to MathProc Base. Pajarito would need to be updated to MathOpt interface, so basically it would just be a matter of doing that. But there was one question about, or a couple of questions about Pajarito, where it was like, is it Julia based? And it's mostly Julia based, but it also needs to call a mixed integer linear programming solver and a continuous solver. And at that point, both of these would be calling external solvers that were not written in Julia. And in particular, one of the solvers we relied heavily to make Pajarito work well was actually using Mosaic as a conic interior point solver, as a conic continuous solver. And Mosaic is extremely stable and really good. Pajarito would probably not be as effective without it. But it's not written in Julia. And the other thing is that it only uses the standard cones. So cones that are sort of like a small number of cones that through the bridges can model everything else that MOI can model, but you need to add formulations that potentially are more complicated. And I'm going to give you a precise example in a few slides. So I guess after the last meeting, the second jump dev, Chris, around July 2018, was like, well, what about making a pure Julia-based continuous solver that doesn't need to do the reformulations, that directly deals with all the cones that MOI could deal with and more. And so I would say these was like a chicken and egg thing on adding more cones directly to Math interface was part of like happening all at the same time. And of course, I'm not an expert on continuous optimization. Chris was not an expert on continuous optimization, but Julia makes you bold. So let's just do it. And we started working on that. And basically that's how Chris got started on Hypatia. And Chris named it Hypatia because Hypatia was I guess a Greek Egyptian mathematician who liked conic sections and actually designed an astrolabe, which is technically an analog computer. So she likes computers and cones. Perfect name for a conic optimization solver. And started working over the years. So then Leah Kapelovich also joined the team and started working on this. Some of the first presentations on this happened on the third Jump Dev workshop, which happened in Santiago last March. And I would say at this stage, Conic was sort of like very centered on what was being done in the Jump world. So again, there's these two talks that were directly related to Hypatia. So I also want to mention a few more. There were more, but one of the interesting ones is tulip.jl, which is an interior point solver only for linear optimization that uses a lot of interesting features from Julia using abstract linear algebra, for instance. And perhaps one of the interesting things about this solver is that it's the only pure Julia solver, as far as I know, that has been included in the classical optimization benchmarks by H. Middleman. So that's an interesting thing. It's competing with LP solvers or LP codes that are written in C or more classical languages. Then Benoit also introduced a lot about the set programming stuff that actually is on his thesis. And another thing that I wanted to mention is Julia Moments, which basically is the dual of the sum of squares and gives an interesting moment measure interpretation to polynomial optimization. That again, if you go to Benoit's thesis, you can learn a lot more about that. So in the, so I remember how much time I have. So I guess in the last few minutes, I wanted to actually tell you, I'll dive a little bit deeper on what Hypatia is doing and what conic optimization, like what the interesting things you could do with conic optimization inside Julia. And I'm going to go, basically one of the things I want to talk about in detail is barriers, because I think there's an interesting potential there for extra development. But I'm going to go sort of like high level. And again, if you want more details, we have a paper that will explain this, and hopefully there'll be more, Hypatia will be released soon. So there'll be more interesting, more details there. And so what is Hypatia? It's an interior point solver. It's based on, it's a homogeneous interior point solver. So it's based on an object called the homogeneous self-dual embedding. And it works for standard cones or also more exotic cones. So standard cones like semi-definite programming, or basically all the cones that Mosaic can work with. And in addition, you could do things like the sum of squares is actually a cone. You could tackle the sum of squares cone directly without needing to go through the semi-definite cone. And you could do even slightly more crazier versions of the sum of squares cone. So a matrix of where each entry is a polynomial that is a sum of squares of other polynomials. And these kind of objects you can use to, for instance, restrict the trajectory that I had before to be convex, or add other types of shape constraints to trajectories. And it has about 24 predefined cones that a Hypatia can deal with directly. So like slightly more like going beyond what like is currently directly accessible from MOI. And in addition, it allows you to actually add a new cone. So if there's a new cone that was not included, you could bring it. And the main question is, well, how do I add a new cone? And the way to add a new cone is through an object called the barrier for the cone. And I'm going to discuss that in the next slide. And by having this wide number of cones and potentially additional cones, you can take advantage and basically write down formulations that are much smaller, will take less memory, and potentially will give you a computational advantage on solve time. And there's a lot of extra interesting things in Hypatia as well related to Julia. So it made it very easy to add multi-precision arithmetic, to use abstract linear operators. So if we needed to do things that were sparse matrices or very structured operators that actually could potentially give you a big advantage, easily switching from direct solvers to indirect solvers and things like that. That unfortunately, I guess I won't have too much time to cover. So, but I said barriers. So the key for interior point work algorithms for conic optimization to work well is in part the strong theory of barriers for conic optimization. I mentioned the homogeneous self-dual embedding that I skipped, but basically one of the keys is if you pick your primal dual pair, after some transformations, you can basically deduce that solving the optimization problem is equivalent to following a dynamical system that's described over here. And this dynamical system basically has some linear equations, some nonlinear equations, and some extra constraints that end up being not too terrible, because if you actually focus on these and started in a place that was a good place, following this trajectory closely will keep you inside these constraints. So this is linear. So the key is basically what are these nonlinear constraints? And these nonlinear constraints or nonlinear equations are based on, you get one for each one of the cones you're considering your formulation. And this G function is basically the gradient of a barrier for the cone. So I'll read the long name in a second. Let me maybe show an example. So for instance, if I want to look at the set or the cone, which is the non-negative ray, let's say for dimension 1, it's basically minus log of x. And you can see that basically what it's doing is it's finite valued inside the set. And the closer you get to the boundary, it shoots up to infinity and doesn't allow you to actually leave the set. And so that's why it's a barrier. But in addition, it has a lot of extra properties. It's a logarithmic homogeneous self-concordant barrier. And I won't go over the details of what it means, but it gives you a lot of theory and a lot of properties that you can exploit on the interior point algorithm. And it could be as simple as minus log of x for the non-negative ray. If you have a slightly more complicated cone like the log determinant cone, you get a slightly more complicated barrier. But the key is, if you want to introduce a new cone, the only thing you need to do is figure out what the barrier is, a logarithmically homogeneous self-concordant barrier, for that cone is. And this could be an expression, it could be a function, it could be a Julia function. It could actually be Julia code. It could be as complicated as you want, as long as you can give that Julia code for the barrier and you check that in fact all the necessary properties worked, you can plug it into Hypatia and Hypatia will be able to use it. And in particular, if you just plug the function, Hypatia could use automatic differentiation to actually get the gradient. For some of the cones, we actually use that at first. Then we kind of tweak for some of them, we tweak them to improve a little bit more the performance. But again, even if this was not an expression, it was a complicated Julia function, you could just plug it in and Hypatia will use the AD tools inside Julia to basically calculate the gradients and do the appropriate discretization of the dynamical system. Why do I care about having more cones? I mentioned that more cones allow you to do more natural models, or at least more smaller models. So let me show you only one example. So this is a problem called the optimal experimental design. And basically what it's trying to do is trying to design a linear regression experiment that will give you a predictor that has the minimum variance. And you can recognize something here that looks sort of like a Fisher information matrix. And what this problem is trying to do is basically trying to minimize some function of the eigenvalues of the matrix. So let's say a function of the determinant would be the product of the eigenvalues. So we're basically, this function is ends up being the covariance matrix of the estimator that you're designing, or the regression experiment that you're designing. And so this is what you would write sort of like in math. And if you want to write it in conic form, you basically just need to use the log det cone square from MOI, and you get a formulation that looks almost exactly as the one you wrote at the beginning. Now, this requires actually using the locked cone square. So if you actually, that is not available directly in MOSIC. So if you wanted to use MOSIC directly to solve this problem, MOSIC understands the semi-definite cone and the exponential cone. You can rewrite this problem for those cones by adding extra variables, extra matrix variables, and writing all this. And this is basically something that the bridges in JUMP and MOI will do automatically for you if you actually need to. The only problem is that you added these extra variables, and now you have a problem that is significantly larger. And this could actually cost you in memory, in speed, and in solvability in general. So here's some experiments that are slightly outdated on Hypatia, but still kind of give you the general idea of what's the power of having these slightly smaller formulations here. And here we're comparing Hypatia solving this smaller formulation, Hypatia solving the big formulation that would have been constructed through the bridges, for instance, and MOSIC solving the formulation that it can actually, again, it's the same one, but it's the only one that it cannot go directly. MOSIC would not be able to solve the natural formulation directly. And we can see that I was actually quite pleased that Hypatia could get this close to MOSIC on the same problems, because MOSIC is extremely advanced and has a lot of improvements that Hypatia doesn't have. So we got close. Of course, we couldn't win, but if we could actually solve a much smaller problem, now we had an advantage, and we could actually do a lot better in speed than MOSIC. And in fact, if we keep going and in other problems as well, at some point MOSIC will run out of memory, and Hypatia can keep going and solving more problems. And again, this is primarily thanks to the reduction on size. And again, Chris and Leah worked a lot on actually making the code stable, because even just writing a completely pure vanilla version, it would still be hard to actually beat an advanced code like MOSIC. So not entirely sure how early on, but I guess it's like this is mostly what I wanted to talk about. So if you want to know more about Hypatia, we have one paper that is available. The repo and an update to the paper and another paper hopefully will come up in the, let's say, next couple of months. I didn't mention Conic optimization at JUMP Developers Workshop number 4, which was supposed to happen in June of 2020. It was unfortunately canceled due to COVID as well. So I don't have a lot of examples on Conic. I will say that Yuri Nesterov was scheduled to give a plenary. So I guess Conic was still being sort of front and centered in JUMP developers, in the JUMP developer world. One other thing that I wanted to say is like if you have interesting applications that you use on JUMP, either academic, real world, anything that where JUMP was useful, we're trying to collect all that information. So please let us know. Please email that to Oscar, his Northwestern email. And finally, one parting thought is like, so one of the things I mentioned, Julia makes you bold. It allows you to try out new things without necessarily diving deep. So first is like, that's how I basically started learning. I still would not consider myself an expert in continuous optimization, but now it's trying this has allowed me to actually dive deeper in the subject, and it was very interesting. So I would suggest use it as a way of trying out new math and new techniques before you see if it's really worth diving and learning on them. But do dive and learn a little bit more. Don't use it as an excuse just to blindly use the code. Once you're convinced that it works, dive deeper, peel the onion. That's what Julia was designed to do, to peel the onion and go deeper, both in the code and in the math. So with that, thank you very much. It's been hopefully it's been somewhat instructive, and I'll make sure the slides are up somewhere so you can follow the links if you want to learn more about any of the topics. So thank you.
Thank you, Juan Pablo. We've got a couple of questions from the Discord chat. The first one was, how do you feel about how macro heavy / DSL like JUMP is?
So basically, that's an interesting thing that, so in essence, this is like, I would say it's somewhat of a deep question of what are the right oracles for optimization? And the more natural oracle is functions. Functions are mathematical objects, and functions are programming language objects. And that's a very, very one-to-one. In Conic optimization, for instance, the objects are sets, so it's a little bit harder. There's not a one-to-one, and that's why you actually need a a little bit of a DSL. There's the affine part, which is an affine function, and that you could potentially integrate it more. But you really get to the stage of function when you go to the barriers. So in some sense, there's an issue there is like it's hard to really make the belongs to match between the math and the Julia code. And I would say that's the reason why you need this extra DSL on top of the code. So it's in some sense, at least that belongs, it will be somewhat necessary to have it in some way, potentially as a DSL. Maybe there's an interesting solution, but I would say that's the crux of the problem.
That makes sense. Referencing, I think one of the slides, maybe 4 or 5 slides ago, the question was, how general is the cone here? Are positive semi-definite matrices a cone? Are polynomials positive on index 0, 1 a cone here?
Yes, so it could be very, very general. So I guess like a polynomial, what was the polynomials? So I guess non-negative polynomials, for instance, would be a cone. It's like infinite dimensional, so I guess you would need to restrict it in some way. If you have a positive semi-definite matrix and you want them to coefficients to be non-negative, you could intersect it with the positive definite cone with the non-negative variables. And again, you can combine cones, or you could find a better barrier for that particular cone. And if you can find a better barrier that satisfies all the properties, you could plug it in. So you could really go crazy with the hard part of being able to put the cone is really getting the logarithmic homogeneous self-concordant barrier for the cone. That's where the hard mark would be. But besides that, you just want it to be a convex cone that is closed. And that's about it.
Awesome. And really quickly, the closing question that I have for you, are there any key features or hurdles that the jump team that you all are trying to overcome before doing a 1.0 release of jump?
Very good. I guess I would attribute it to the, I would expect that if we actually had the jump developers workshop, we would probably be at 1.0. So I won't claim this is anything official, but it's we're close. It's the distance has been, so I think I almost always say this every time I talk at a JuliaCon. I say by the end of the year, but I'm gonna say it again. Let's say by the end of the year. Hopefully it'll be a little bit earlier.
Awesome. Well, thank you. I appreciate your time today, and everyone join me in thanking Juan Pablo for this awesome talk.
Thank you very much.
And Vic, I believe this is the end of our live stream for today.
Yes, it is.
So we can cut this off. Thank you everyone for tuning in. We appreciate it, and we'll see you at the next live keynote tomorrow.